differentiate both sides, right?
Right.
So that differentiation is like what is that? Like, is it so in this case, so 7x squared will be, if you differentiate that, then it would be like delta, du, or like the function 7x squared over dx.
Very good question. Okay, so it means that there is some sort of confusion concerning the notation.
Yeah.
Right. Okay. So if I want to differentiate 7x squared, there is only one variable, and x is the independent variable. The answer is 14x. If you want to write that f of x equals 7x squared, then you can write f prime of x equals 14x. That's one option. The second option is d over dx of f of x, which means the derivative of f of x with respect to x, which is still 14x. You can use this notation for 7x squared, but we really don't use it like that, but you can. So you're differentiating 7x squared with respect to x, and you get 14x. Is that better? Okay, so now when I go back to the problem, then I have to differentiate this as a product and this as a product. But it has minus in front, so it also has 2 in front. I refuse to keep the 2 inside, because I make my life easier if I leave the 2 outside to wait for me. The constant can wait. So I differentiate the first function, I get 1, so then times the second function plus x times the second function prime, which is this. And I'm done only with this portion. Is this clear? Okay, now minus. Again, I don't want to bother with the sign. It can wait for me. I differentiate the first function, I get e to the x arc sine y, oops, and plus e to the x times arc sine y prime, which is 1 over the square root of 1 minus y squared times dy over dx. And then equal symbol, 14x. Now let's think, is this okay? So 2 is outside. The first function prime is 1 times the second function plus the first function times the second function prime. We just had that a few minutes ago, right? Y squared prime is 2y dy over dx. Then I'm here with minus. E to the x prime is e to the x times arc sine y plus e to the x times arc sine y prime, 1 over 1, a square root of 1 minus y squared dy over dx. And the right-hand side is 14x. Is this clear? Are we okay so far? Yes, Tony?
I just want to double check that I understand. The second side is e to the x times 1 over the square root of 1 minus y squared times d to the dy over dx because of the chain rule, right?
Because of the chain rule. Because arc sine of a function is 1 over the square root of 1 minus the function squared times the inner function prime. Correct. Very good. So then I'm after this. But I still have another step before I get to that. I distribute 2 to y squared plus 4xy dy over dx. I distribute negative 1. I will leave this and this on this side, but I have to move this, and I have to move this to the other side. So I will factor out dy over dx, and I have 4xy minus e to the x square root of 1 minus x squared dy over dx equals, these become positive. No, I'm sorry, this becomes positive, e to the x arc sine y minus 2y squared plus 14x. And final step, this over this. And I will not bother with it any further. So dy over dx is 4xy minus e to the x over the square root of 1 minus x squared, and the top is e to the x arc sine y minus 2y squared plus 14x. Any questions on this? Any questions? Yes, Thomas?
Can you slowly do the derivative of the 2xy squared?
Yes.
Okay, so that derivative is the whole thing change of that, right? Over
This is the first function, this is the second function. I have to write the first function prime times 2 plus the first times the second function prime. It's a product of two functions. First function prime is 1 times the second function, which is y squared, plus the first function, which is x, times the second function prime, which is 2 times y times dy over dx. It's the chain rule combined with the power rule. I bring down 2, subtract 1 from the power, times the inner function prime. So for y squared prime, I'm using a function to the nth power prime, which is n times f to n minus 1 times f prime. N, f to n minus 1, 2 minus 1 is 1, times the inner function prime. Is that okay? Yes? Better? I recommend everyone redo all problems we did in class with implicit differentiation and practice with the recommended homework and check the answer in the back again. Thomas, are we okay now?
I need to take some time to think about how from the definition of the chain rule right here to how you.
It's combined with the power rule. If you're only looking at the basic definition of the chain rule, it's not enough. It's a combination of the chain rule with the power rule. Okay, so when I have a function, if I have x to the 4th power prime, I have 4 times x to the 3rd times x prime. But x prime is 1. That's why we don't write it. So if I have a function raised to the nth power, I have n f to n minus 1 times the inner function prime. So that's why y squared prime is 2 times y times dy over dx. 2y dy over dx. It's a combination of power rule and chain rule. Anything else? Okay, before I forget, we meet tomorrow, Tuesday, in this room from 4:15 p.m. to 6:15 p.m. I hope you can make it. You cannot? I know, Thomas, you cannot because of work, school, or both, and you cannot make it tomorrow.
I have work. Are you going to post a video of it?
Of course, all the time. And I can meet with you after class on Wednesday for half an hour to sit down and show you what we did. Okay? So don't forget tomorrow, 4:15 in this room till 6:15. Okay? Now I'll wait till 4:15 4:20 if that's what you want me to do. Is 4:20, 6:20 better? I have a class that starts at 6:30.
Yeah, 4:20 and 6:30.
I can even wait till 4:25 to 6:25. That's fine too. I just need to end by 6:30 because I have the other class. Okay, very good. So let's continue with 3.6. Derivatives of log functions. So when we differentiate, so this is 3.6, when we differentiate natural log x, the formula will be 1 divided by x. That's the rule. What about natural log of a function of x prime? What would you say? Yes, Tony?
It's 1 over u in this case, and du over dx in this example.
Very good. Times u prime. Perfect. Now the question is, what do I do when I don't have natural log, but let's say I have log base a of x? And I would like to discuss this before we come up with the answer. Do we remember what it's called, the change of base formula? Change of base. So let's say I would like to determine log base 3 of 5. Yes, the more sophisticated calculators allow you to put in 3 in there in the base. But my calculator, for example, does not have that feature. My calculator only has 2 possibilities. It has log, which is base 10, and it has ln, which is base e. This is not a sophisticated calculator. So assuming we don't have those sophisticated calculators, then I will have to change this into either log, which is base 10, log base 10, and you'll tell me what it is, or natural log. So notice that this is a ratio of 2 logs. So the log at the top is of what? Of 5, indeed. And the log of in the denominator is of the previous base. And these will be the same. This number will equal this number. So I'm coming back here, and I will say that log base a of x is the ratio. You can use this, or you can use this. I would like to use this because I already know natural log x prime. So can you translate this into base natural log, base e? Excellent. Natural log of x over natural log of a. Good. So now this is a constant. So all I have to do is differentiate that, which I have. It's right here. So then the answer would be 1 divided by x times natural log a. So if the base of the log is anything but e, then we're going to have to use this formula, or this differentiation rule. So if it's just natural log prime is 1 over x. But if I have log base a of x, then it's 1 over x natural log a. Okay, so these are your first 1, 2, and this formula. So please put them in if you want to have them on the handout. Now I would like to talk about this one. So let's take a look. Natural log of the absolute value of x prime. Now let's start with the absolute value of x. Can anyone tell us the options for the absolute value of x? What are the possibilities? Yes, if. Excellent. Or perfect. If. Excellent. So now I would like to present this function. Can anyone tell us how to write it? The first option would be ln x. If x, and I cannot use 0, remember the graph of natural log is this, has a vertical asymptote at 0. So now when I apply log to this, I can no longer have 0. And what is the other option? Very good. For x less than 0. Perfect. Okay. So now I'm ready to differentiate. So the natural log of the absolute value of x prime will be what did we say natural log of x is? Prime is. Perfect. And now I need to differentiate this. But now this is not plain x. It's natural log of a function of x. This is no longer plain x. So how do I differentiate natural log of 1 over negative x? 1 over negative x times the inner function prime. Negative 1. Perfect. So then, what will you say? Look carefully and simplify this for me. I'm going to write it again. So natural log of the absolute value of x prime is 1 over x for x positive, and is what? Exactly, for x less than 0. So now you will say, forever, the natural log of the absolute value of x is 1 over x. This is very important for chapter 5. This is a very important result. So now you have this answer as well. It's 1 over x. Now all this is a section by itself. All section 3.6 is a section by itself because of this. What it's called logarithmic differentiation. And then we have to look at two limits. And then we can continue. Okay, ready? So the next title is logarithmic differentiation. So we had implicit differentiation, now we have logarithmic differentiation. What is that? And why is it used? And why I need it? It's because when I want to differentiate this, I cannot. No rule. I can differentiate x to the third, which is 3x squared. I can differentiate e to 5x squared, and I get e to 5x squared times 10x. But I cannot differentiate sine x raised to tangent x. No rule. You know, differentiate a function raised to another function. So let's start with this example. Since we picked I picked this, I just made it up, and then we can look and choose problems from the. Yes.
But isn't like 5x squared a function?
Yes, it is.
So,
But the base is a number.
all right,
It's not a function.
never mind.
E by itself,
It's a constant.
it's a constant. Exactly. Very good point. So I have only one way of dealing with this. So our function is f of x equals sine x raised to power tangent x. And we want to find f prime of x, or y prime, or dy over dx. And I know what Tony is going to say next. He's going to say, you're just playing with us. No, I'm not. But I'm going to use y right now. I'm not going to use this, and I'm not going to use this. I'm going to say y or f of x are the same, so I'm going to use this notation. For the same thing, it's still our function f of x. So I'm going to apply, since I cannot differentiate this, I'm going to apply, what do you think, to both sides. And let me give you a hint. Log, indeed. I'm going to apply log to both sides. So I'm going to say natural log y equals natural log sine x raised to tangent x. So you can say now, okay, wait a minute. You're asked to differentiate y. why are you applying natural log to both sides? And my answer would be, bear with me, I'll explain. Now, is there anything that I can do to the right-hand side? There is nothing I can do to the left-hand side. But is there anything I can do and I'm allowed to do to the right-hand side?
Wanna bring tangent x in the front?
Absolutely. That becomes a factor in front. And now you know why I applied natural log. Because the left-hand side is natural log y. The right-hand side is tangent x multiplied by natural log of sine x. And now I can differentiate. What type of differentiation is this? Implicitly, yes. This I can differentiate because it's a product of two functions. This I can never differentiate. There is no rule for a function raised to a function prime. And then you can say, and what are you going to do at the end? You'll see what happens at the end, and we will still be able to find y prime. Okay, so the left-hand side. How do I differentiate the left-hand side? Not sufficient, because y is a function. Now I will use dy over dx, indeed. The right-hand side, remember, is the first function, the second function. I have to use the product rule. If you like my order, fine. If not, just use the method you like. The first function prime. Tangent prime is the other one. Yes, tangent and secant go together. Cotangent and cosecant go together. So the first function prime times the second function plus the first function times the second function prime. I just learned how to differentiate log of a function. What do I write? It's on the handout. You have it. 1 over sine x multiplied by, very good. Perfect. Okay. Okay, so I'm going to copy again everything I have. So I have 1 over y dy over dx equals secant squared x times natural log of sine x. Let's see if we can figure out what this is. So this is tangent. How much is this? It's cosine over sine. How do we call that? How much is tangent times cotangent? Tangent times cotangent. 1. Very good. Good. What am I solving for? What is the variable here? What am I interested in? What am I after from all this? Exactly. Of course. dy over dx. So what do I do to both sides to get dy over dx on one side? Alone. Careful. Multiply both sides by. But what was y? Raised to tangent x. And this is implicit differentiation. We were not able to find the derivative of this function without applying log to both sides first. So from this step to this step, we multiply both sides by y, but instead of writing y, I copied the function. Okay, so let's work on a few on page 223. You can choose from homework if you want. You can choose any problem, even problem, whatever you want. Let's work on a couple. And then I would like to come back here and talk about these two limits. Would you like to choose, or I will?
Number 7.
Number 7. Okay. I was hoping you would choose something, a function raised to a function, but that's okay. Let's do this first, and then we choose that. Good. So normally we don't write base 10. I don't know why they wrote base 10 in there. It's clear. So I'm going to copy like that, but we normally don't write base 10 by convention. So we are asked to find f prime of x, which is maybe on the handout I should have added here log base a of u of x prime, and this will be 1 over u of x times natural log a, and at the top you should be u prime, either here or here. Okay. So 1 over u of x times natural log a times u prime, or you can put it at the top, same thing. So what do we write? Yes, 1 over x cubed plus 1 times natural log very good. And the top or multiplied on the side, doesn't matter, same thing. 3x squared. You can condense it, and I recommend that. 3x squared over x cubed plus 1 natural log 10. I would like to choose among problems, I should have indicated that myself, among problems from 43 through 50 on page 223. Any preference? Anyone? Okay, I'll choose 48. We have y, which is sine x raised to natural log x. We're asked to find y prime. What will be our first step? I'm asked to differentiate a function raised to a function. Yes, so natural log y equals natural log of sine x raised to natural log x. Good. What will be the second step? Yes, natural log x becomes a factor in front. So natural log y equals natural log x times natural log applied to sine x. Can we now differentiate both sides? Yes. How are we going to do that? What type of differentiation is this? How do we call it? Implicit differentiation. Let's differentiate the left-hand side. Very good. Equals? Yes, times natural log of sine x plus, yes, times, yes. Let's try and condense it a little bit if we can. Any questions before we continue? So 1 over y dy over dx equals natural log sine x over x plus, what is this? How do we call it? Yes, plus natural log x times cotangent x. Good. So now I'm ready to find dy over dx. What should I do to both sides to get the derivative of this function, which is sine x raised to natural log x by itself? What should I do to both sides? Yes, multiply both sides by y. So this is sine x raised to natural log x, and this is natural log sine x over x plus natural log x cotangent x. And no, you cannot simplify. You shouldn't even bother with it beyond this point. Any questions? I want to talk about a theorem that I did not put on the handout. It's called L'Hopital's French, L'Hopital's rule. It is applicable only in two situations. Only in two situations. One situation is 0 over 0, and the second situation is infinity over infinity. I know we did not get examples from all situations, but how many indeterminate cases are there? It's okay if you don't remember, there are 7. 7 indeterminate. Seven indeterminate cases. They are listed in the limits handout, in case you're wondering where I mentioned them the first time. So here it is. On the last page of the limits handout, here they are. 1, 2, 3, 4, 5, 6, 7. So L'Hopital's rule is applicable only in the case 0 over 0 or infinity over infinity. And these are the cases if I'm able to change them into this or this, then I will be able to apply L'Hopital's rule. So what is L'Hopital's rule? I haven't mentioned what it is. Okay. In the case of limit as x approaches infinity, let's say, of x squared plus 1 over 3x squared plus 2, we have to determine this limit. And what is the first thing we have to do? Always plug it in, right? So where is the top going? Good. Where is the bottom going? Correct. So then, is this a case in which I could apply L'Hopital's rule that I haven't even explained yet? Yes, it is. It's this situation, correct? So L'Hopital proved, this mathematician proved that in these two situations, if you want to determine the limit, you can differentiate the top and differentiate the bottom. Remember, this is not the quotient rule. It has nothing to do with the quotient rule. And we are only talking about limits. So I can determine the limit of an expression if in the situation of infinity over infinity or 0 over 0, only applying L'Hopital's rule, only not applying the quotient rule, but only doing this, differentiating the top and differentiating the bottom. Before we do that, can anyone from previous experience, can anyone say what is this limit? The degree of the top is 2. The degree of the bottom is 2. So what would be the horizontal asymptote? the leading coefficient over the leading coefficient. So the answer will be 1/3. Okay, so let's continue. I differentiate the top. What do I get? Not with the quotient rule. We've never done this. That's not allowed to differentiate a function like this. But this is not a function that I'm differentiating. I'm using L'Hopital's rule in the case infinity over infinity or 0 over 0. So what is the derivative of the top? Perfect. What is the derivative of the denominator? Perfect. Now I can say, fine, I'll simplify x with x, and 2 over 6 is 1/3. Here's another example for you. What about limit as x approaches 0 from either side of sine x over x? What does this equal to? We can never forget this limit. 1. Perfect. Let's say I don't know that. So I plug it in. What do I get at the top when I plug it in? Good. What do I get in the bottom? Good. Is this a typical situation in which I could apply L'Hopital's rule? Good. So then I have limit as x approaches 0. What is the derivative of the top? Very good. Excellent. What is the derivative of the bottom? 1. And one more time, let's plug it in. The answer is 1. So this mathematician showed that only for limits, in the situation infinity over infinity or 0 and 0 over 0, I can differentiate the top and differentiate the bottom, not applying the quotient rule, and I get the same answer. Okay, I need this result in order to finish up this section. So I would like us to determine these two limits. They are very important limits. So I have limit as x approaches infinity from 1 plus 1 over x raised to x. This looks awful. My first step is I'm going to denote this by what? What do you think? Here's your hint. Exactly. Of course. And before that, I should have asked you, please plug it in. 1 over infinity. As x approaches infinity, we have this result from chapter 2. What does this equal to? Perfect. How much is 1 plus 0? 1. How much is, so this will go 1 raised to infinity. So let's come back. Do we know anything about 1 raised to infinity? No, we don't. We're stuck. I have no idea what the answer is going to be. I only know that 1 to infinity is an indeterminate case. Okay. So then, now, what do you think I'm going to do next? I cannot apply L'Hopital's rule. I have no idea what to do. I denoted this by function y, and then it's in this section. So what did we do in this section? We applied natural log to both sides, of course. Apply, natural log. Good. So natural log y equals natural log of 1 plus 1 over x raised to x. Okay. Now what? What do you think I'm going to do next? Exactly. Natural log y equals x times natural log of 1 plus 1 over x. There is no mentioning of differentiation. We're just trying to find the limit. Okay, ready? So now I have the limit of this function, but now I have the natural log of this function. I'm going to find the limit of this. You could say, wait a minute. The problem is asking you to find the limit of the function, not the limit of the natural log. Yes. But if you remember, I said there is a very important result. I'm looking for my other handout for chapter 2 handout. If you have it. I pulled it out to have it handy, and of course now it's not handy. You can find it. I want you to look at that handout and tell me in a minute or two, in a minute or two, which super important result we are going to use. So I'm going to say, yeah, I know the problem is asking me to find the limit of the function, but I'm going to stretch it a little bit and find the limit of natural log y. So this is the limit of this. As x approaches infinity from x times natural log of 1 plus 1 over x. I'm going to try again, because now I want to determine this limit. So what does this approach? Good. What does this approach? Just this. Good. What does this approach then? How much is 1 plus 0? And how much is natural log 1? Natural log 1. 0, correct? So you can say, what did you accomplish? You changed this indeterminate case from 1 to infinity into 0 times infinity. So what did you do? Nothing. I accomplished a lot. This, changing this into this, brings me closer from changing this into one of these two and applying L'Hopital's rule. Okay, so let's see. So algebraically, I'm going to manipulate this, and you'll tell me whether it's the same. When I flip this, do I get x times natural log of 1 plus 1 over x? So instead of writing x in front, I brought it in the denominator, to the denominator is in the form of 1 over x. Is this the same thing? Because if you say this is not the same thing with this, then I can continue. Are they the same? We agree? They are the same. Now let's see what we have. Now, what is the limit from the top? Yes. What is the limit from the bottom? Yay! What did I do? I changed this ugly indeterminate case into something that is a little bit more user-friendly, into something that is very nice. Why is this very nice? Not only because there is hope, right? Because then we were talking about factoring, it's a different story. But why is this nice? Because I can apply L'Hopital's rule. So I will differentiate the top. It's 0 over 0. So can anyone give us the numerator prime? We also discussed, allow me to refresh your memory, I'll come back right here in a second. We also discussed the derivative of 1 over x, and I said this is so useful to remember, if possible. I don't want you to just sit there and memorize it, but what is 1 over x prime? Let's say I don't know. Well, it's x to negative 1 prime, which is negative 1 times x to negative 2. Very important result. It will make your life so much easier if you would remember this. Okay. Right? It's x to negative 1 prime. I bring negative 1 in front, and I subtract 1 from the power. So now here, can anyone give us the numerator prime? One over 1 plus 1 over x times the inner function prime. What is the inner function prime? Very good. Over the denominator prime. Remember that in these situations we're not using the quotient rule, and this is the only time in which we're not using the quotient. Right. Here's what I'm going to do next. I'm sure you are anticipating this. They are the same. They're going away. And what is the answer then? As x approaches infinity, where does 1 over x go? 0, so yes, 1 plus 0, so this is 1. Okay, so let's go back. What is 1? Here's what is 1. The limit of natural log y is 1. So I'm going to copy just that. The limit of natural log y is 1. And now I want to come back to that super important result that I mentioned several times already, which is right here. The swapping of operators theorem. So I'm allowed to swap the operator. So the limit of a function is the function of the limit. So how can I swap the operators here? What will you tell me to do? What operators I'm talking about? I'm talking about this operator, and I'm talking about this operator. So please swap them and tell me what to write. Of? Okay, so now I'm coming back to what I'm asked to find. I was really asked to find the limit of y. I was really asked to find this. What do I know? I know that natural log of blah is 1. So how much should blah be? And then I have the answer here. Natural log of is 1. Exactly. So the limit of y must be e. So this is e. Because only natural log e is 1. There is no other number whose natural log will be 1.